Hi. So this is actually a project, a tool that kind of came out adjunct to SciPy because we were having some performance degradation issues there. So what problem is it trying to solve? Well, there's this thing called Wirth's law. This is Dr. Wirth, and he said back in the 80s that software expands to fill all available memory, and software is getting slower more rapidly than hardware becomes faster. This does tend still to be true today, and probably even more so with Moore's law, at least at the single core level, slowing down and what have you. Why does this always happen? Well, you write a new tool, you say, hey, come along, use my new tool, Frobulator 1.0. It's simple and lean and elegant, and it's 3 times faster than any other frobulation package that's out there, okay? Because you just wrote it. It's really clean and fast, and you put all this effort into making sure it was clean and fast and lean. And well, then you send it out there, you get some bug reports. It's seg faults on invalid input. Okay, now you got to check that invalid input and make sure that it doesn't seg fault. It doesn't work on Windows. Okay, it's got a special case this and that for Windows. It doesn't work with complex numbers. Okay, so now you have this separate code path for complex numbers versus rational numbers, right? Oh, there's no Unicode support. Okay. So now you were happy in ASCII, but now you have to make sure it works with all these foreign characters that Americans never care about. It's not compatible with legacy frobulator tools. So you write a whole layer, to make it backward compatible and more people can use it, right? So you do all this. Now you release version 2.0, we fixed a gajillion bugs, and you can frobulate with confidence that nothing's going to break, okay? But now your machine looks like this. And first bug report you get, well, it's 20 times slower on my data. It uses twice as much RAM, right? This all just kind of happens because you're concerned with fixing the bugs, not maintaining the performance, right? So this isn't really progress. So along comes Airspeed velocity, and its purpose is to help you track the performance of your project over time throughout its source code history. And as I say, it came out of the SciPy project. We had a story very similar to the one I just told, only different in the details in the units package. So here's how it works. You go in there and you write a bunch of benchmarks, and they are just very simple little functions. They look kind of like unit tests in nose or py.test, if you're familiar with those. And they're just very simple things that will exercise something in your code that you're concerned about becoming slower. And then Airspeed velocity will run those benchmarks over the history of your project. So if you give it the command ASV run, and you give it a range of commits, version 2 to master, it will check out each revision. For each revision, install it into a virtual environment, run all the benchmarks you defined on your project. By default, it uses the timeit algorithm in the Python standard library, and it's available in IPython. So it automatically determines the number of repetitions it needs to do, kind of does it once and then estimates, I need to do this a few thousand times to make the timing accurate enough. Only difference is, unlike the built-in timeit algorithm, it actually uses processor time, so other processes on your machine will not impact the performance. The timeit by default in Python uses wall clock time. And it's actually a new feature in Python 3.3 that I've backported to work in earlier versions. So this is what it ends up looking like when you have some results. And these are real results from SciPy. So here on the x-axis you have time. These are the date of various commits in your project. And the y-axis is the speed of the particular benchmark at that time. Over here you can select from all the benchmarks that you've made, so we can look at this one. You can run them on multiple machines, and each machine will get its own line. You can run it in multiple versions of Python, and you can turn those lines on and off if you want. Python 3.3, in my experience, always seems to be about 10% slower. Very interesting result. And you can plot them on a log scale, or you can say I plot it relative to a reference point. You click this point, and then everything is relative to that reference point. If you click on any of these data points, it will bring up GitHub and show you that commit, so you can see, what code change may have introduced a particular slowdown. Hopefully, okay. And so that's basically the gist of it. It's a pretty simple little tool, but I'll get into some of the more detailed features next. Just to talk a little bit about what it is not, which I think helps clarify what it is. It's not a unit test framework. So like unit test or nose or pi.test. Those things tend to work really well when you want to do a binary pass or fail, is something working or not. They don't do very well with this fuzzy, something's getting worse, and I care if it gets worse, but I don't care if it just gets a little bit worse. That kind of fuzziness where you really want to have a graph of what's going on. Those tools don't address that very well. It's not a profiler, so it's not going to tell you why something is getting slower, right? You still need to use a separate tool. I'm not reinventing that wheel to answer those questions. It's not a profile visualizer like RunSnake or Kcachegrind. Again, just those tools already exist in Python. They work pretty well. Why reinvent that? And it's not a comparative benchmarker. There's a tool called CodeSpeed that's used by the SciPy project, which is really about comparing PyPy versus CPython versus some other, stackless Python, some other implementation. But it doesn't really track the behavior of a single project throughout its lifetime. So again, slightly different problem space. The thing it's most like is this thing called vbench that Wes McKinney wrote for use in pandas. And it actually pretty much shamelessly borrows from it. However, vbench, it's a little hard to get up and run. It just takes some time to getting used to. One of the goals of Airspeed Velocity is to try and make it as easy as possible to download it, start using it, writing benchmarks for your own project. And another feature that it has that vbench doesn't address very well is the data, the results are just stored in JSON files in a Git repository. So it's very easy to have multiple people with different machines contributing results to the same dashboard, essentially. There's sort of no one database that you have to have live with a lock on. You just throw a bunch of junk into your Git repository and it all works. It also has no server-side component at all. So it does create these nice websites that everybody can see, but it's all static HTML and JavaScript. So you can put it up on GitHub, on GitHub pages, or any of the number of free website hosting things without worrying about security and keeping things running and paying for computation time. It's pretty easy to write benchmarks where the API for something has changed over time. You just simply put your functions inside of an if-else block. So here's an API that changed earlier on in AstroPy. If it's before this version, we want to do this one. If it's after this version, we can do this one. And then they'll all get plotted in the same benchmark. Besides just tracking runtime performance, it can also track memory usage. So it may be that you have some object that used to only take a few bytes per object, and now suddenly it's holding on to all kinds of references and not leaking memory, but just sort of hogging memory in ways that are new. So you can write memory benchmarks. All you have to do is make the object and return it. And it uses a library called heapy, which tries to sort of estimate the amount of memory that a Python object is using. And it actually calculates the incremental cost of each object. So often in Python, two objects will reference the same things, and that's fine because each additional object continues to reference those same things. Heapy will actually try to calculate what's the incremental cost of each new one of those objects. You can also track anything you want. So if there's some other feature that's not time or memory, but you want to track how that's going, maybe the number of units that your library supports, you could track that over time, and it'll build a graph for you. All you have to do that is you return a numerical value. It also integrates with profiling tools pretty well. So you've plotted these graphs, you've seen that it's getting slower, you want to figure out why so that you can fix it. The ASV command just has this profile thing where you give it the name of your benchmark and a tag in your repository, and we'll go ahead, check that out, build it in a virtual environment, and pop up the profiler to start investigating that. So this is, again, a real-world example. It'll profile your benchmark and then bring it up in run snake run. And you can tell just by looking at those two different tags, clearly the time here is going somewhere. And by drilling down in run snake run, you could start to figure out why and which one of those new features that you added is contributing to all the extra runtime. It also does something that is very similar to git bisect. So it may be the case that you have so many historical revisions in your project, it's just not practical to test every single revision, right? So you subsample some number of revisions in the past, and then you say, I want to figure out which exact revision created the regression. So if you have a range that looks kind of a bit like this, that's mostly monotonic, it can actually go through and do a binary search to find the single revision that created the most regression within that range. Now, the proviso there is you're assuming it's monotonic and you don't know that. If it happens to kind of go up and down, it may find you the wrong commit or a commit that's locally bad but maybe globally just fine. So this is what that looks like. Again, you just give it a range of commits and a benchmark you want to run, and it draws this pretty little picture, you know, starting in this range, and then it tries over here and tries over here based on the binary search until it finally gets down to a particular revision that led to the regression. There's some ways in which it would be nice to make this more generally applicable, but you know, one of the things about this kind of testing and benchmarking, the results really only apply to a particular machine and hardware and software configuration, right? So if you upgrade your machine, either just the software or maybe you put some more RAM in it, the new results you're going to start generating are not comparable at all against the old results you had. Now, it's easy enough to just go back, regenerate all the results. That's generally the solution to that. But you do sort of want to keep a machine that's not going to change too much so that you can keep regenerating your results. For similar reasons, it's hard to run this kind of thing on something like Travis CI because you never know what machine you're going to get there. So the results obviously are never going to be comparable. It includes a plugin system, so any sort of feature that's not there, you can probably write a plugin for and add it. So this is just some ideas of plugins that may get written in the future. The bold ones already exist, and the other ones are things we might want to add in the future. Right now it only works with Git, but again, that's a plugin, so you could write a plugin for other kind of repository systems. For the hosting and how it links to the commits, it understands GitHub natively, but you might want to write a plugin so you work with Bitbucket or some other sort of code hosting system. These are the benchmark types it deals with. It currently can only build things if your project has a setup.py with standard dist utils and you can install it with pip. If you have something that's more C-oriented or what have you, you'd probably have to write a plugin so it understands make files or whatever it is you need to do. Where is it going to go? Well, it needs to release a 1.0. It's probably at that point. We've been using it in AstroPy. It's been pretty helpful finding some things already, but we need more testing on other projects to kind of find the holes and missing features. It would be nice to have parameterized benchmarks. So one thing it can't do is ask a question. So with small data, how fast is it with larger data, and then with even larger data, run benchmarks where the input can change and then be able to graph that in a way that you can compare. It doesn't do anything like that, but that's, I think, something that's very near the top of the to-do list. There's no sort of aggregation of results right now. It would be helpful to just have a one graph that's an aggregate of all the benchmarks in your project, so you could just see, in general, how are we doing. It'd be nice to run these on a cluster. It is rather time-consuming to run a significant subsampling of the AstroPy history, for example, takes 3 days on my desktop machine. It would be nice to somehow fan that out. The problem is you have to have pretty homogeneous hardware to do it, so you'd have to have something you control that is not changing, so the results are useful. It'd be nice to have an alert system. So right now with AstroPy, we generate new results every night for all the new commits in that day, but there's no sort of automatic reporting of, this benchmark doubled that overnight, you might want to have a look. It sort of assumes that people are going to look at it periodically or look at it before a release. And it would be also very nice to do what Travis CI does with unit testing to run the benchmarks on a pull request before it's even merged. So you could say, here's this new feature. What is the performance impact of it before actually merging? That's, again, a tricky problem, because running just arbitrary pull requests on a machine, you have to run it in a virtual machine for security, but then you're running in a virtual machine, and the benchmarks are going to behave differently. So that's a research problem I'd like to solve. And that is it. I'm available for questions.
Thank you, Mike. Please give Mike a round of applause. So for questions, if you put your hand